Good afternoon, and welcome to this time of the CAUPA Acorn Fund presentations. And today we have two presentations, one from the CAUPA Part IIB Undergraduate Award, and another one from the Blue Sky Award to a postdoc. And the first presentation will be given by Egle Augustaityte. I hope I got the name right. And she's a Part IIB student, just graduated. And the title of his talk is Plastic Sand Bricks, Optimization of Materials and the Mechanical Properties. Egle.
Thank you. So thank you for introduction. I will share my screen. Can I just check can you see the screen? Is that clear?
Yes.
Awesome. So thank you for introduction. As I say, it's Egle Augustaityte. No one really gets ever my surname correct. And the topic is plastic sand bricks, optimization of materials, mechanical properties. And my supervisor is Dr. John R. So starting with the problems, plastic pollution in the ocean is a significant threat to wildlife and humans. A large amount of this plastic pollution washes up on shores of many coastal countries in Africa. One such region is Takungu village in Kenya. Takungu village, like many, does not have a proper waste management system. Moreover, in some African countries, construction material is expensive or unsustainably sourced. For example, in given Takungu village, buildings are built using sticks, clay, and mud, or coral bricks. And coral brick house is shown in the figure. Coral bricks have a very harmful effect on the environment because coral mining sites experience a reduction in coral variety in coral reef fishes. These problems have encouraged local people in affected regions to develop construction material out of plastic waste. One way of doing this would be, first example would be eco bricks on the top left, which is done by taking a plastic bottle, PET plastic bottle, filling it with shredded plastic, and then stacking on top of each other. This is a very simple solution, however, lacks construction mechanical strength. Another way of doing this is by extruding molded plastic into Lego brick shape, so into brick shape. And the examples would be recycled bricks, precious plastics, or by block. And the last way, or third way of doing this, would be mixing a molten plastic with sand and then making tiles or bricks. And the examples are already implemented in Gambia and Kenya by ganja makers and waste aid. The last approach is research worldwide in other papers, and performance assessment shows a potential to be used in buildings. Hence, I focus on the last approach during my project. During my project, I researched three main areas. So firstly, I wanted to pick the plastic, decide on which plastic I will be using. Secondly, develop safe manufacturing process. And third, finding a way to optimize material strength. First, the research currently mainly focuses on LDP plastic. Thus, there is a research gap on performance of a HDP plastic and a combination of different plastic types to make these bricks. LDP and HDP were selected as they both melt below 130 degrees and burn above 300 degrees. Hence, give a wide range of temperatures to safely operate at without burning plastic. And moreover, they're also miscible plastics together, so can be combined. As shown in pictures for my project, HDP shredded bottle caps, black LDP recycled granules, and sharp concrete sand were used. Moreover, after performing a literature review, it was noticed that even though there is existing research on plastic bricks, it lacks explanation of how these bricks are actually made. Therefore, I also aim to develop a safe manufacturing process that could be performed by the average skilled person in a remote village. Many existing manufacturing methods use firewood to make their blocks, as shown in the figures. However, firewood burns at a much higher temperature than the melting temperature of most thermoplastic polymers, which can cause parts of the plastic to degrade and release large amounts of toxins, and could be seen by white fumes in figures. Therefore, an oven for closed die forging rig method was implemented as temperature is better controlled. The process of making samples involved weighting plastic, placing it into oven, then every 15 minutes mixing mixture by kneading it like a dough, as it was the only way I could mix plastic and sand together without burning it. Once mixture is adequately mixed, I place it into molds and position on the compression rig. The samples are then compressed by tightening the bolts until excess starts coming off. Currently, most of the projects mentioned before, so like precious plastics or recyclable built and others, focus on using bricks as cavity walls or paving tiles. However, with my project, I wanted to assess whether they can be used as a standard construction material and answer the central question: are plastic sand bonded bricks a viable construction material for low-rise residential buildings? 3-point bending and compression tests were performed using an instrument machine to calculate compression and flexural strength. As seen from the graph on the left, for HDPE plastic, the optimal ratio where compressive strength is highest is given as 30 to 70, meaning 30% plastic. And sorry, I think some of you are not muted. That was just a bit distracting me. But I will continue. So the optimal ratio is given for HDPE plastic is given as 30-70, meaning 30% plastic and 70% sand, which giving maximum compressive strength equal to 37.3 megapascals. The graph on the right shows that for LDPE plastic, the optimal ratio is 20-80, meaning 20% plastic, 80% sand, and the maximum compressive strength is given as 25.2 megapascals. In all HDPE samples, the compressive strength was above 26.4 megapascals, and in all LDPE was about 20.7. This is important because, according to the British standard, for clay bricks to be used in 1- to 2-story buildings, compressive strength should be above the 9 megapascal. Hence, experimental results show an excellent possibility for plastic bricks to be used in buildings, as all of the samples have a compressive strength significantly above the 9 megapascal requirement. As mentioned before, there is an optimal ratio at which compressive strength is highest. This happens because with plastic proportion below 30%, there is not enough plastic to cover all sand particles, which lump plastic together, causing brittle failure, which lump sand together, causing a brittle failure as seen on the picture on the left. With plastic proportion above 30%, there's plastic excess. This means that compressive strength depends more on the plastic than the sand, hence lower. Therefore, as shown in the picture on the right, at around 30%, there is enough plastic to cover all sand particles and not have access to achieve maximum strength. In the same picture, it provided bigger grains, broken in half, indicate a strong bond between plastic and sand. The variation in the results are caused due to following aspects. So first, sand grain size. Bigger grain size particles positioned closer to the edge, as shown in the figure on the left, reduce the compressive strength by initiating cracks earlier than expected. The importance of the grain size and the results is also reported in other research, and as is shown in the graph on the right, that the strength decreases with increased particle size. This is the consequence of increased porosity. Hence, the variation in the results could be reduced by picking sand with smaller grain sizes. Variations are also caused by creep. It was found for HDPE plastic that the reduction in the results after more than 4 weeks between tests was up to 2.2%. Although this is a slight change and could be caused by other factors already mentioned before, it should not be neglected, as this could have an important implication over time. For these bricks to be used safely in a building, the creep effect on the material should be researched more further. Lastly, air bubbles in the samples affected the compressive strength of these samples. It was found that in increased plastic content, there was an increase in air bubbles trapped in the material as seen in the picture, where air bubbles are circled in red. In conclusion, plastic bricks are chosen as a great value and construction material out of waste. During this project, a safe manufacturing method was developed, 3-point bending and compression tests were performed on different ratios. All samples' compressive strength is above 20 megapascals, hence the experimental results showed an excellent possibility for plastic bricks to be used instead of clay bricks or other bricks in low-rise buildings, as all of them had a compressive strength significantly above the 9 megapascal requirement. Thank you for your attention.
Thank you very much, Egle. Now the presentation is open to questions or comments. I'll start. I have one question, Egle.
Yeah.
When you now reach quite a high strength level, so how tall you think you can build a building with this plastic sand bricks?
It's an interesting question. I mainly was focusing on the idea of building 1 2-story buildings. So mainly only research on the requirements for these buildings, which was 9 megapascal. That being above, again, this is another question that I think I should look into more, is where does that 9 megapascal come from? And does that also, what's the error in there given? Because potentially maybe for plastic, even though the plastic bricks and clay bricks, they actually weigh almost the same because of sand. The plastic bricks are not, people would expect that they are much lighter, but they actually weigh pretty much the same weight. So I would assume that the needed compressive strength would be similar. So I think it then just depends on, the requirements or the British standard, and then adjustment over time.
Yeah.
Thank you. Any other questions?
I have a couple.
Yes,
so
please.
following to Professor Chu's question, I'm actually thinking when you build a taller building using these bricks, maybe the brick itself is not the limiting factor. It could be the thing that you use to glue them together. I don't know.
Yeah, so that's a good point. I think, just want to show, I think the idea of these bricks, what's the difference between, let's say, clay bricks and these bricks, if we're just, comparing them together, is that this is you can melt them in any shape you want. So the idea is that you probably could just choose a mold that you could, use somehow to stack them together, or that you could maybe add some steel bars in between. I mean, this is another part. I didn't research as far as this wasn't part of my project, but I think the idea is that because it's melted plastic, you can melt it or extrude it, the mixture, into any shape you want. I just made those samples because the testing, so the freeform bending adapter was designed for this shape.
I have another question regarding the plastics, because whenever we use plastics, I think it's also a very recent thing about the microplastic particles. So do you know if we're using these bricks, like where these bricks, degrade and release a lot of microplastics into the environment, or is there anything to do to actually study this part even?
It's a good question. I think the problem with microplastics in general is it's a very, it's a topic that everyone seems to sort of know a bit. But I think there is, in general, when I tried researching it more, and I'm not sure if maybe someone can help with this, it seemed to be that it's just sort of, everyone knows it's a problem. No one really knows how to stop that. And I think the way my approach into this was that, because I'm talking about recycling plastic. I'm not talking about making a new plastic just to make this. I'm thinking of what's the way to interlock plastic so that, we would remove it from the environment. So I think if you think about which one is worst, the way I would consider was that it probably would be worse to leave plastic in landfills to sort of degrade them and, move to the, make the degraded plastic move to the oceans or something like that. I think that, so the idea was that, you sort of take something and place it into a building. I think the consequence, if I would think about that, would probably be similar as having a plastic outdoor furniture. So it's sort of, it's degrading, as I would assume that it will be some microplastics released, like, from any plastics there are. I just don't know if there is any other solution to sort of make it that there wouldn't be microplastics. And I think this is just a whole new research.
Yes, absolutely. And one extra thing that I think it might be an advantage of these plastics and bricks is, I wonder if the thermal conductivity of those materials compares to the standard brick, because it might be, I don't know, it might be better in like energy efficiencies of the building using bricks, which is an extra advantage compared to the normal building materials that we're using.
Yeah, that could be. Plastic is quite, could be the one stopping the barrier for the heat exchange.
Thank you. Any other questions? I have another quick one. How do you consider the fire safety?
So Actually, I think I did find, I mean, again, it's not part of my research, but when I was thinking of other, there's, other things that people could be researching. Sorry, I think I had a slide, maybe just those steps.
Okay.
It's just like future work sort of idea, but there are, so the test I did, because of the lack of time and everything, was mainly compression and flexural strength. I didn't discuss flexural strength just because it takes lots of other time and it's not as important as compression strength for bricks. But I think the other researches that did was how degradable they are, what's the creep, and then flammability. And I think they found that flammability, so I think that flammability is they are, the way they organize are in sort of A, B, C, D classes, I think. I mean, from what I remember. And I think these bricks performed in between A and B class. So it wasn't, it was sort of, because the plastic in itself, it doesn't really burn, it more melts. I mean, when I was trying to burn plastic, usually just sort of starts degrading, at least maybe those recycled granules. So yeah, I think the problem would be if there's a fire in the house, they might start melting, but potentially there might be a way to solve this.
Okay, yeah, I think it's still, you have a lot of future works in this area. Right, any further questions? If not, let's thank the speaker again. Thank you, Egle. Thank you very much.
You.
Right, now I think it's the time for our second talk. This talk will be given by Jenny Nian Jiang, and this is a Blue Sky Award talk, and the Blue Sky Award is to be given to postdoc researchers and for a longer period of research. And the presentation, the title is Exploiting Nonlinearity in III-Nitride Semiconductors for full spectrum detection by up-converting infrared and down-converting ultraviolet to visible light. Jenny, please. We can see your slides.
Thank you very much. And this is a very long title, but I think the focus is really exploiting the nonlinearity of III-Nitride semiconductors. So first of all, just talk a little bit about the motivation and where the idea is from. So right now, we all need to, typically need to detect the spectrum from the deep UV light all the way till the far infrared light for different applications, and different light reveals different information to us. So we're currently having different detectors for different part of the spectrum detection. And in quite a few industry, like food industry, Earth observations, it actually benefits a lot if we can have one detector that can detect the whole full spectrum. So right now, it requires different detectors, but the idea comes in, instead of working on the materials used for the detector itself, how about we engineer the signals that come in? So it comes to how about we convert the UV light and IR infrared light to the range where it can be detected by a, like a CCD detector, silicon-based detectors. So that's the idea, that's the motivation. So why do we choose gallium nitride? So gallium nitride has really wide band gaps, and also gallium nitride is the simplest in the III-Nitride family semiconductors. So the wide band gap can make sure that it doesn't matter what light, like instant light or emitting light, that we're dealing with, it minimizes the absorption by the material itself. And also it has decent refractive index. So the refractive index is a very important parameter for the materials when we're choosing for the nonlinear applications, and we're typically looking for high refractive index materials. So as we see from the plot down here, that the gallium nitride has the refractive index is not as high as silicon or gallium arsenide, which has been studied quite a lot by scientists. but they're not that, they are decent, they're still like above 2, so it's still good. And also the production of gallium nitride gets cheaper and cheaper thanks to the vast applications that it can be used in our daily life. So just a very brief introduction of the nonlinear wavelength conversion about the physics. So this is different from what we call a 2-photon absorption, that the material absorbs 2 photons, so it produces enough energy to jump above the band gap and then re-emit as 1 photon again. Is different from that. This is actually more in the, instead of in the quantum mechanics field, it's more in the classic physics part, that the photons got confined in such a small volume in the material and interact with the material and then combine together. So it's different from a little bit different from what we're usually talking about, semiconductors and band gap stuff. And this was firstly discovered in 1961, and since then it has been widely used in laser technologies. So if you have a very powerful laser in the lab, you probably have one of those crystals in your laser to convert the laser wavelength from a single one to multiple wavelengths. And you would know that they're typically, the crystal itself doesn't come really big, but to make sure the crystal works in perfect situation, the laser itself becomes really bulky. So as always, we want to minimize, like we want to make things small. So I was personally inspired before I came to Cambridge that my friends were working on the meta surfaces, that they start talking about night vision goggles, just like the sunglasses that we're wearing every day. So in this approach, they're using nanoparticles arranged in a certain way, and as a thin film that can convert light frequencies from infrared to the visible range. And the efficiency is not as high as we would like it to be, partially because of the semiconductors gallium arsenide band gap is not that wide, so it will absorb quite a large part of the visible light. So compare these two, well, bulk material exists in nature. They have very weak intrinsic nonlinearity, and to achieve the frequency conversion, they need to meet the phase matching conditions, which brings a lot of restrictions to where and how we can use it. As we just see, the laser is very bulky, so where you can use it is very limited. And the nanostructures provide a lot of advantages. First of all, it can break the limit of the placed on the bulk material by mere resonance or the bond state in continuum, where the efficiency can really approach very, very theoretically to 1. And it also frees us from the phase matching conditions. And also because it's not a bulky big crystal, so it can be very flexible. We can make it into thin film. We can even, the shape doesn't have to be rigid, and we can modify the filling fractions to change what we want to get. And also, I think, which concerns, I think, us engineers the most, is what is the efficiency. So this actually can dramatically increase the conversion efficiency. So now we kind of talk a little bit about both. So I would like to talk a little bit more about gallium nitride into this nonlinear world. So if this thing is so good, why not a lot of people, or why it hasn't been fully explored? Because gallium nitride material has been there for a very long time, and a lot of people know it these days, or whether they know it or not, they actually is in their daily life because the LEDs we're using. So gallium nitride is a material that does not exist in nature. So it's a man-made material, which means that we actually don't have a substrate, a perfect crystal substrate to grow further perfect crystals on it. And these materials typically come with a lot of defects, point defects, which we can't really visibly to see those defects, but there are lots in it. Dislocations, as we see the in the TM pictures, and inverse domains, which means that the range of the atoms can change directions, depends where you are. So all of those things, with all of these defects, gallium nitride is still functioning and is still making a very important part of our life. And when it comes to the nonlinear world, where we typically deal with, we would like to deal with perfect crystals because the properties of a perfect crystal is a lot better known. And also it's kind of like easier, I think in a lot of cases, it's probably easier to create a crystal with no defects rather than control the defects. So for this case, so gallium nitride with all the defects, it actually brings a lot of opportunities in this nonlinear world. So I will talk about this a little bit further as we're going down. So anyway, to start the work, the first step is we need to get the gallium nitride. And I work on nanowires. We have bulk materials, and the bulk material, as we just mentioned earlier, have a lot of defects, and it's hard to isolate the impact of those defects. So one thing good to do is to do the nanowires where we can actually isolate defects and then study the properties. So there are typically 3 different ways of making gallium nitride nanowires. So the first one is silane assisted growth, which is a growth method that requires no treatment before we put the wafer into the reactor to get the structures. However, the growth on the substrate is not as well controlled as the other 2 methods. So selective area growth, where we actually have to get a planar gallium nitride structure as the template to grow on top. And then after that, by putting the masks in, we can control the shape and the position of the structures. And another method is called selective etching, where we actually etch down from, so we create nanowires from the planar structures. So for this particular method, we have more freedom in what kind of shape do we want to create. However, this method is limited by the quality of the planar structures. So I started my work in Cambridge just before, or actually right at the beginning of the pandemic, which means the access to lab facilities is limited to me. So when I plan for my work, I have to factor all of this in to choose the one that actually get me the results fastest, which is the silane assisted growth, because it involves the least steps before the nanowire growth. So this is just a diagram to show the summary of how we achieve the gallium nitride nanowires in lab. So gallium nitride growth compared to other semiconductor growth, the growth environment for gallium nitride or for III-Nitrides is a lot harsher, and also we do not have a very wide window. So it's a game playing on the fine line to find the right structure. So as soon as we get the structures, we're planning for next steps. So we have these structures, we can do simulations on what are we expecting, or is there anything that we can get out of it. So we performed the simulation using COMSOL on a single nanowire structure. Was a little bit too fat to be called nanowire. Microwire probably is more appropriate. So we simulate when we have the incident light, the polarization of the incident light, the electric field can be parallel to the z-axis or to the x or y-axis. So when we did the simulation, we do realize that when the electric field of the incident light, when it's parallel to the z direction, we actually get a stronger interaction with the material. So this scattering cross-section actually shows a linear property of the material instead of a non-linear property. However, it's an indicator of what we can get. So we do see 3 resonances in the infrared light region. And for different wavelengths, we got different Q factors. So the higher Q factor, the stronger signal that we would get. So we know that in this wavelength range, we could perform the measurements. So here is the setup of the when we do the nonlinear measurement, which happened in the advanced optics and photonics lab in Nottingham Trent University, who actually worked with before I came to Cambridge, and they also moved from Australia to UK, which makes things a lot easier for me. So we have a laser that has a very wide wavelength range from 160 nanometers to 2000 nanometers. And so this is a simplified light path of this setup, because we have to put in a lot of filters in so that we're measuring what we're really interested in, rather than all the photons from the laser went into the spectrometer. So the setup is actually fairly simple. And before we conduct the measurement, so I did the SEM to actually know what the sample that we're looking at, because in the measurement, as we can see, the only thing we see is a 90 degrees view, and it's an optical microscope. So the structures that we can see, or the information we can get there, is very limited. And it's nanowire, so it's not like planar structures that you can assume everywhere is uniform. So we did SEM pictures at a 0 degree view, which we can correlate with the view that we get from the setup, the experiment setup, and also 30 degrees view, so that we get more information about what the structures that we're measuring. So here I'm going to just talk about 2 nanowire measurements that there are a lot, and we did a lot, but I'll focus on this too. And here it's just a higher magnification of the pictures to show how the wires look like. So they are standing, well, before we break them down, they're standing on the sapphire substrate. So here is actually what we see from the CCD camera. The yellow circles that we've seen here is a marker for where the incident laser is at. So the reason that we place this there is because we actually can't really see the laser when we work at the wavelength of 1500 to 2000 nanometers. And then by exposing the structures, we actually see pictures on the CCD, which means they're emitting at a visible wavelength. So we know that we can measure something. So then we went on to more detailed measurements to find out where the resonant wavelengths are. So for the standing structures, so this is a 30 degree view of the wire. So when we do the measurement, is actually as we shown earlier here, is from so the light is, okay, we can put it, the light is parallel to the length of the structures. So we did observe 2 resonances from the wavelength between 1500 to 2000. So the first one, so here we see the wavelength is mostly around 750 nanometers, which is a second harmonic generation from the incident light of 1500 nanometers. And the other one, which is much stronger, is from 1800 nanometers emission. We measure the polarity because we want to get a bit more information about the emission of from these structures. And so they are mostly circular polarization, but with when it's for the 1800 nanometers, the shape is not quite round. And we still need to look into it why this is not a round symmetric shape. It shows some information that we need to decode. So the much more interested part is actually the measurement from the wire that was laying down on the substrate. Well, first of all, we see much stronger emissions from both resonances. And for the 1800, well, when we're trying to find out the resonance around 1800, we can even see the third harmonic generation here. And the reason we didn't see anything before, like, at wavelength even shorter than what we've seen here, is actually because the filter that we're using is a short pass filter, but it actually blocks all the light away from 620 nanometers. So we are still waiting for a better filter so that we can see more third harmonic generation here. So one thing that is very interesting here is that the two resonances got totally different polarities, and the polarity is about 90 degrees rotation to each other. So this actually, together with the very strong emission, we have some theories about why they're so strong, and we are still working on consolidate the theory. So to date, the signal that, or the information that I want to show to everyone here is that we have achieved quite strong second harmonic generation and third harmonic generation from single gallium nitride micro rods. The theory, we believe that it is because that we actually have multiple resonance modes confined in the single nanowire, and some of these resonance modes actually interferes with each other and create this quasi bond states in continuing state, which means the efficiency of the nonlinear conversion can be improved dramatically. And the next step is, now we learn what happened in single gallium nitride micro rods or nanorods, where we, for different sizes, we can perform a lot more study over there. And also, what if we pull, instead of just one single structure, we put an array of those crystals together, and what we can achieve. So those are all very, very exciting things, and we have done some preliminary simulation results showing that we can definitely get some nonlinear conversion from the arrays, but yet, yeah, so we are fabricating this metal surface takes a lot more time than I thought, because etching gallium nitride is a lot more challenging than we think, and the key chemicals that we need to use here, sorry. So the key chemicals that we need to use for the reactive ion etching process, we do not have it in engineering, and we are.
Please mute so that. Yes.
Yeah. So because of all the restrictions for what we can do here in Cambridge, this part of work actually been really slow. However, it is happening with, I just managed to get help from collaborations to access everything that we can find. So what I want to say is that I'm really glad that after such a long time study, we now really see that gallium nitride or III-Nitrides is actually a promising candidate to make these metal surfaces. And really, this is just a start, and there's so much more we need to find out, and so much more we need to learn. And as the first time when I gave a presentation for Blue Sky Award, I said this is a real blue sky project, because I'm really looking for establishing something, and I think it definitely has. I think I feel lucky, because even though the gut feelings were there, but this is the first time that we actually see that this can come to real life as something that is really exciting. So anyway, at the very end, I would like to thank all my collaborators. So the Joyce group here, I have a master student who actually worked on the etching part of the project and recently graduated. And to the Gallium Nitride Center in Cambridge, where I get all the gallium nitride materials, and my collaborators from the Australian National University, where
Is there somebody
what happened?
editing on the screen? I thought that this was not shared, that there's no whiteboard. Okay.
Yeah, so my collaborators from Australian National University, so they are the experts in the nonlinear physics world. I'm a material scientist, so I learn from them. and my collaborators in the Nottingham Trent University who are experimentalists who are working on the nonlinear measurements. So I think one thing that I would like to say here is that even though the light path setup looks very simple, but actually to get results, it took me 3 trips up there to actually finally get to the point where we actually can measure the signals that we need. So huge thanks to all of them. Without them, I would not be able to do what I have presented here. So thank you very much, and questions.
Thank you very much. Yes, indeed. Any questions? Jenny, I think it's fantastic to see the first light coming out from the second and the third harmonics. Yeah, it's really fantastic.
Yes.
Yeah.
Yeah,
and
we are all very excited when we first saw this. It
yes.
was because everybody have this thinking of, you know, maybe it wouldn't work because we haven't really, like previous studies on gallium nitride on bulk materials, the emission is not very strong anyway.
Yes.
But yes.
Yes, this is fantastic. Is there any dependence on the shapes of it, the size, geometry?
Yes, so the size definitely. So the size actually will shift the, so I think I can show the simulation at the very beginning. So when we change the overall size of the rods, we will shift the resonance modes, you know, the wavelength will change.
Yeah.
So that's one thing. The absolute shape, for example, you know, is hexagonal here, or is a round, or rectangular, or square shape.
Что он делает? Он ебанутый, что ли?
Okay, please go on. I don't know what's going on here today, but yeah, I
Yeah,
think
so,
that only make it more interesting. Yeah.
Yeah. So the shape is not. The shape itself doesn't have as much impact as the size. Put it that way.
Yeah.
However, as we see, I think another very interesting thing about gallium nitride is because of the, you know, the crystal itself, because it's not like a cubic crystal. So when we have the structures standing up or laying down, it means that the internal electric field is totally different. So this actually brings some flexibility of what we can do.
I think
Thank you.
Really
Thank you. Yeah, so it's the size, and also I think what we want to explore a bit further is that right now the simulation we're happening, it's like a 2D simulation, so it can only deal with the structure with exactly the same diameters everywhere. But what in real life we often have the nanowire with diameter that is changing along the length, and how that's going to impact the whole thing is something yet we need to find out. Personally, I feel like that's probably not a bad thing, but we still need all the theory to back all of those things up. And I feel like if we have dramatically change diameters, we might be able to convert a wider wavelength, like wider range of wavelengths instead of a single wavelength, which we've seen already over there is actually, so that might be because our wire is not that uniform across the whole length. And one thing that is very interesting that I found out is that as a material, like a semiconductor material scientist, we always want our material to be perfect. No defects, you know, uniform diameters everywhere. But working with gallium nitride and in the nonlinear world, I actually realized all the defects that we're trying to get rid of might be something good for the applications in the nonlinear applications. So it's very interesting and exciting, and a lot more needs to be done, put it that way.
Yes, the reason I'm asking this is to see whether you would like to pattern instead of uniform, the array with uniform diameters for your rods could have different sizes, and then so that you can convert a wider band range. Yeah.
Yes. So that's definitely something that I think it doesn't matter we want it or not. I think when we do the top-down method, creating the structures, we probably were facing very tapered structures, and we would like to see what we get out from there. Yeah, the shape is always something that I'm always interested on, what the shape does to the final results. Yeah, so it's a lot of things. A lot of things, yeah.
Any other questions? I think Denisa has a question. Yeah,
yes, I was wondering if we can use plasma etching to prepare gallium nitride pillars.
Yes, yes. So typically when we're etching gallium nitride, we use chlorine gas. So it's the reactive ion etching, but we don't have it in engineering. And all the other etching plasma that I've looked at, this structure is so this material is so stable that it's actually not easy to etch it. And the most effective way of etching it is using chlorine and metal mask materials. And these two means I can't do it in Cambridge, because the only place where we have, well, the only place that I found who has the chlorine gas do not allow us to put metal in. So that was part of the reason why the etching part has been really slow.
Thank you.
Thank you very much. Any further questions? If no further questions, let's thank the speaker, Jenny, for the very nice talk, and thank both speakers to come today to present their result. Thank you very much, and thank you for everybody for attending this presentation. So we're looking forward to further results coming from your work and to other Acorn presentations in the future. Thank you very much.
Thank you.
Thank you.
Thank you.
Thanks.
Thank you.
Thank you very much. Bye-bye.
Okay, bye-bye.